Hi, today I would like to present our work on modeling and symmetry vector fields using higher order energies. And maybe let me start with a short clarification. So the object of interest in this talk are tangential and rotational symmetry fields on curved surfaces. That means fields where at each point of the surface we have n vectors exhibiting an n-fold rotational symmetry. So, for example, the fields from the first talk would be then 4 fields, or we abbreviate those as n fields, so they would be 4 fields with a unit norm constraint at every point. We can visualize these fields in different ways. In our talk, we will stick to 2 visualizations, like on the left, where we show one n vector per triangle, or on the right, where we show some integral lines of these fields. So the goal of this talk is to provide a n-field modeling tool, so a tool that allows users to intuitively create such fields in real time. And a prototype of this tool is shown here, where the user edits a curvature-aligned 4 field on this rocker arm mesh, and he can use these hard constraints to edit the field in any type of detail. So the tool has some design principles. First of all, we want real-time responses such that the user gets immediate response to his interaction, which requires us to be able to solve for smoothest end fields in a matter of milliseconds. We want the tool to be intuitive, and for this we think that using some modeling constraints, namely hard interpolation constraints on directions of the fields or singularities, are very helpful to get a direct control over the field. Furthermore, we would like to provide local editing. That means that the user can select sort of a region on the mesh and edit inside that region without changing the field outside of it. Finally, to be also more intuitive, we would like that if the user only slightly changes directional constraints, for example, the field also slightly changes, so sort of a smooth dependence on these constraints. The power of such a tool can be seen here, where the user on the left designs two fields on this bunny mesh, and the directions are then used to guide these stroke directions in a painterly rendering of the bunny. So both parts of this method are interactive, and as you can see, the user has like this direct control. He can change these little details on the bunny's eyes, and the rest of this field aligns as smooth as possible. So, of course, there are many more applications for such a tool. So one I've just shown is this non-photorealistic line arts. 2 fields can also be used to guide anisotropic shading, which I will show later in the talk. 4 fields can be used for texture generation, painterly rendering, image stylization, surface segmentation. Of course, 2 prominent or prominent applications are the generations of quad meshes, as we've seen in the last talk, or hexagonal parametrization. Of course, our fields can be used as inputs for such methods, but we do not aim directly at integrable fields, so this is not a key application. One mathematical aspect of these tools are M-harmonic or higher order energies, and these energies are required actually for using the types of constraints that we are proposing. So as an example, we see here that the user edits a 2 field, and here we use the normal, the harmonic energy. So when he puts this singularity constraint, as you can see, the influence of these constraints are very local, and the field does not globally align to them. And what's worse is that when we refine the field, the solution, like the influence of this hard constraint, becomes even smaller, and you can see the solution depends on the triangulation, so we do not get consistent solutions. Using biharmonic energies, however, so higher order energies, like here, you can see that the field globally aligns to the hard constraints that we set. And what's more is that when we refine the field and refine it more and more, we get to we converge to something like a continuous solution. So before we get ahead of ourselves, let's make some basic definitions. So we work with n vector fields. So the at each point we have an n rotational symmetry vector that is a set of n vectors which exhibit this 2 pi over n-fold rotational symmetry. Here we see an example of a 2 vector or a 3 vector. So as we've seen in the first talk, it's sometimes very difficult to deal with a set of n vectors at each point, because that requires us to sort of keep track of the matching between these vectors. So one idea that has been proposed was to use a representation vector. So how to choose this representation vector, I will show on this 2 vectors. So let's say we have a basis defined that allows us to define the argument, for example, of this vector v, and then we simply choose the representation vector to be the vector that has twice this argument. So now you say, yeah, but why did you choose v? You could have chosen minus v. Okay, so let's choose minus v. So this is the argument of minus v, and now the observation is that twice this argument is the same angle modulo 2 pi, so we end up at the same representation vector. And this sort of holds for all 2 vectors, and when you replace the 2 by an n, it holds for all n vectors, and this is also a bijection. So every representation vector corresponds to a 2 vector or an n vector. So this allows us to replace these sets of n vectors with a single representation vector. In our discretization, we work with piecewise constant tangential n vector fields on U. That means we have one n vector per triangle, but like I said, we replace those by representation vectors. This requires us to choose one basis per triangle, and then allows us to compute these representation vectors. One more vocabulary is that we call fields, n fields that exhibit a unit norm constraint in every point, so that are normalized in every point, as n direction fields. So they are a very important subclass of these n fields. The representation vectors allow us to measure the difference between neighboring n vectors by these quadratic terms, where here the Rij's are pre-computed rotation matrices that sort of transport the vector from one triangle into the other. So then we can measure the differences of the representation vectors and use these as a measure for the difference of the n vectors themselves. This, in turn, allows us to define a harmonic energy, a smoothness energy, as a weighted sum of these differences. And it is very important to choose the weights correctly. We derive this from a continuous model. Using correct weights helps us when we have, for example, meshes like this, where we have a very fine triangulation on the left and a very coarse triangulation on the right, to still get as smoothest fields the correct one. So here the 2 field exhibits exactly this symmetry of the mesh, even though the triangulation is asymmetric, whereas using a combinatorial Laplacian, so where all the weights are 1, leads to a solution that is dependent on the triangulation of the mesh. So the harmonic energy allows us to define the Laplacian, because like the energy is quadratic in the field. There is a unique operator delta such that the L2 scalar product of delta U with U equals to the harmonic energy, and this operator delta is is what we define as the n-field Laplacian. So this can be represented by a symmetric 2f by 2f matrix, where f is the number of faces on the mesh. And finally, using the n-field Laplacian, we can define the higher order energies by raising, in the same scalar product, the power of the Laplacian to the power of m. And the most important case for this is the biharmonic energy that we use in all examples, which takes on the form as written here, where m is the mass matrix representing the scalar, the L2 scalar product. And like I said, this biharmonic energy helps us to properly use our hard constraints. So with this energy in hand, we can finally say what actually happens when the user chooses some hard constraints. Then we generate a field which minimizes this biharmonic energy, plus possibly an alignment energy term, which I will explain later, subject to hard constraints. And in the case of n-direction fields, we have these pointwise unit norm constraints. However, these pointwise unit norm constraints are ill-defined, as has been noticed in the past by Knöppel and others, but they propose a very nice solution for this, which allows a reformulation, which then can replace this pointwise unit norm constraints by an L2 constraint on the field itself, so by a single constraint. And then finally, this allows us to turn the optimization problem here into a sparse linear system, which we can solve efficiently. So now we need to define all the alignment and hard constraints that we have in our system. So the alignment terms are similar to the ones proposed by Knöppel. So for the normal n fields, these are simple difference to a field. So on the right, we can see here a 4-field aligned to the curvature, principal curvature directions. For n-direction fields, so the fields that exhibit this pointwise unit norm constraints, the constraints or the energy needs to be designed a little bit more careful because of the reformulation that I mentioned. So now our hard constraints that we propose in this work, again, for n fields, they are fairly simple. As soon as the user chooses a direction on the mesh, we turn this direction into a representation vector and then simply constrain the field to match that representation vector in this field. And again, for n-direction fields, we need to reformulate this constraint. We do this by enforcing orthogonality with a rotated representation vector. Details can be found in our paper, but we need to be a little bit more careful for the n-direction fields here. Singularity constraints are realized by forcing the vectors around a vertex to perform a rotation. So we do not prescribe the directions of these vectors, but we force them to perform a rotation. Finally, like I said, we allow for local editing. I will not explain it specifically how this works, but we show here what the idea is. So the user selects a region, and inside that region, the field can change. Outside of that region, that field can not change anymore. So I explained all the constraints now and all the ingredients to our system. What I did not talk about is yet how we turn this system into a real-time system. And what we see here are eigenfields of this 4-field Laplacian on this curved bar mesh. And the observation is that the lowest eigenfields of the n-field Laplacian correspond to the smoothest field. So if we restrict our degrees of freedom to these low eigenfields, we not only reduce the size of the system, but we also regularize the field actually, or filter the field to be within the lowest modes of this Laplacian. So as a reduced basis, we use this eigenfields of the n-field Laplace. This makes the system smaller, of course, but it also diagonalizes this smoothness term, and this allows us to repose the system as the Schur complement, which turns the system into a system of the size of the number of hard constraints. So this lets us solve for smoothest n fields very efficiently, and here we can see the comparison when editing 4 fields on this, I think, 300,000 vertex mesh. So on the left, the reduced system, we have a direct response. The field is directly computed and shown, 8 milliseconds per solve, while on the right-hand side, the unreduced system, we have to wait for half a second every time we change the constraints. And when we add new constraints, we actually need for the system to refactorize, which can take several seconds. So another method, or the only other method that is able to create fields in interactive rates, is this method by instant field aligned meshes by Wenzel Jakob and others from 2015. So let me clarify that this method is also able to produce meshes, like quad meshes in interactive rates, which is absolutely incredible, I think. They use a sort of local optimization where they enhance a nonlinear energy iteratively, and they use a multi-resolution scheme, and this sometimes leads to local minima, so we don't get consistent solutions. So in the lower row, you see the solutions of the instant field aligned meshes technique. And we have a different triangulation for the same geometry here, and we get fairly different solutions, while we use this global optimal approach where we get a consistent solutions, even though we use different triangulations. So I mentioned a second application, and here we show this. So the user edits this smooth two-direction fields, and the directions are used to define the directions for bases for ABRDFs, or for anisotropic bidirectional reflectance distribution functions. Those functions are used in rendering to define how light is reflected from the surface. And if this happens in an anisotropic way, we get these very interesting reflectance patterns, and these can now be designed using our tool in real time. And since the field is globally smooth, we get we fill the field and at the places where we did not edit anything in the smoothest way. So with this, I come to two open questions to end my talk with. The first question is, for example, if you have the torus, then on the torus there are two orthogonal fields which yield zero harmonic energy. So these fields should be in the kernel of our discrete n-field Laplacian, but unfortunately, they are not. So there is, for vector fields, so for one fields, there is a discretization which can do this, so which has the correct amount of harmonic functions in the kernel. Unfortunately, we could not extend this discretization for n fields yet. So, and another, of course, very interesting question would be, can we feasibly restrict our modeling to integrable fields, so to fields that correspond or that are the gradients of parametrization, or even to fields that correspond to seamless integer parametrization, which would mean we can instantly use our fields and turn them into quad meshes. But this is, of course, like a very tough question, but a very rewarding one. So with this, I'm at the end of my talk, and thank you for coming here.
Questions?
Thank you. Very nice talk. So I'm wondering, do we have any results with n greater than 6?
Sorry?
For n?
For n equals 6? Yeah, there are results. Sorry, I didn't put video, but in the paper you can see. So 6 we can still feasibly do, definitely. Yeah.
So like how large the n?
Sorry, how large?
How big the n can be?
So this depends on how you triangulate your mesh, but of course there's a limitation due to the triangulation. So the because the types of singularities that can appear are limited by the triangulation, by how many triangles we see around a vertex. Yeah, this I can explain it in more detail later. Yes, but theoretically it's not limited. Yeah.
Is it possible to, in this formulation, instead of pre-diagonalizing the operator, to keep the full operator, but do a low-rank update to the factorization?
Yes. Yes, that's the other alternative. So you can either restrict to the eigenfields, or you can restrict to the eigenfields and actually express the system in the smaller, non-Schur complement version, and do Cholesky updates. I think this is what you mean, right? You can do Cholesky upgrades and downgrades when adding or removing hard constraints. So when changing the constraints, like changing the direction, this is only on the right-hand side. Yeah, so this is the other alternative. But in most cases for us, it was much faster to do the Schur complement. Yeah. Thanks.
Other questions? Okay, well, in that case, let's thank the speaker again.